Start 60. Slight left, good luck. Start 60, slight left, good luck. Five, 4, 3, 2, 1, go. 60, slight left and slight right of the crest, tightens. And 4 left of the crest, keep in 100. Two right, 40. Late, 2 left. And 1 right. And late, 3 left, don't cut. And 2 right, 30. 4 left, half long. And 5 right. Into slight left, slowing, 50. 1 right, tightens, into 6 left. Into slight right. Into 6 left, into 6 right, open to the crest, 40. Left, tightens, into 6 right to the crest, 60. 6 right. Into 6 left, and 4 left, 4 right short. Into crest, into 6 left. Into 5 right of the crest, 30. 3 left short, 30. Short, 4 left, 4 right. And left of the crest, 50. Turn, heavy right. 90. 4 right short. And 2 left, tightens, 30. 6 left, pass junction, into right of the crest. Into 2 right, 30. 3 right short. And slight right. Left, tightens, and 1 right, keep in, 40. Slight right, and 3 left, opens, and tightens, and 6 left, half long, tightens. And slight right, caution to 4 left, into 2 right sharp, 1 left short, and 4 right short, with a crest, into 6 left. 4 right. Into hairpin left. And late 1 right, long tightens. 30. Caution, 2 left. Late 1 right. And 3 left, keep right. To square left short. And 6 right, 6 left. Into 5 right, tightens 3, 30. Square left, tightens. 4 right short. Into 3 left short, 30, hairpin right, opens. 30, 5 right short. Into 6 left, 40, 3 left, tightens, keep in, and 2 left, opens and tightens. Over crest, into 7, 1 right, and plate, hairpin right. 4 left on crest, tightens. And 3 left short, into slight right, and left of a crest, slowing. 30, turn, square right, don't cut, to 1 left, into 5 right of the crest. And 2 left, blocks outside, 60. 3 right, 40. Late, 2 right, tightens half long. Into 6 left, tightens 2, 30. Slight right, 40. 5 left, to 6 right, 60. Caution, 3 right, tightens. Into 2 left short, and 3 left of crest at junction, 60. Left of the crest. Into slight right, slowing to 5 left short, 50, downhill, 3 right, tightens, to 3 left short, into 2 right, 30, late, 1 left, long. starts 5 left, 50. Good luck. Left, 50. Good luck. 5, 4, 3, 2, 1, go. And plate 5 left, half long over crest, 50, 4 right, long, into crest, sudden slide left, 80, crest, 60, 3 right, tightens, keep in to slide left of the crest, 50, 6 right, tightens, to 5 left, short of the crest, 100, 3 left short of a crest, 60, keep right, to 4 left sharp, 100, 5 right of a crest, to 4 left, half long, into 6 right, 60, caution, make 4 right of a crest, 40, 3 left, half long opens, 50, make 5 right, tightens of a crest, 30, slide left, brake, 30, 3 right sharp, small cut, 90, 4 left, to 5 right short of a crest, 130, 5 left short and 3 left, opens, 30, crest, 30, 2 right, opens, into 5 left, tightens 3, cut, and slide right, into crest, slowing, 50, turn, 1 right short, and square right, into 5 left, half long, tightens, square, cut of a crest, 6 right and left of a crest into 2 right and slight left of a crest 40, 2 right through dip to 4 left of a crest 30, 8 4 left of a crest 50, 6 left into 6 right of a crest 60, long crest 40, 6 left short slowing 70, unseen 1 left 30, 6 left, 30, 3 right short, to slight left, and late 1 right, short, into slight left, half long, into 2 right, cut, and 2 left, tightens, and 4 left short, into 5 right, and crest, to 2 right short, to 2 left, to 2 right, and 3 left sharp, and 5 right, into 6 left, 60, caution, late 3 left, short, into 3 right, 30, 5 left, 50, slide right, into 6 left, don't cut, and slide right, and right of crest, slowly, 40, crest, into 3 left short, into 6 right, into 5 left, cut, 2 right short of a crest, 30, twisty, 40, 4 left, half long, tightens 3 for crest, 30, 6 right, 60, brake, 6 right, to slight left, to 4 right, tightens, into early 5 left of a crest, 50, slowing, 1 right, tightens, into turn, 1 left, 30, 5 left, and 6 left, to 5 right of the crest, 100, 4 right short, don't cut, into 4 left, 50, 5 right, very long, tightens, 30, crest, slowing 80. Turn 3 right, tightens 1. 70, crest, 70. 6 left of the crest, half long. To the left of the crest, slowing 50, turn 2 left. LC 30, 4 left, 50, 5 right, half long, tightens 50. 4 right short, pass junction 60, 5 right, tightens 30. Caution 6 left of the crest, tightens 3, half long into crest, so 4 right, 50. Crest to 4 left, tightens and 4 right, keep in. And slight left of crest, 120. 6 right short, through dip, caution, 110. 1 left of crest, cut. 30, 2 right, through dip, to left of the crest. And slight right, 30, long crest. Into late 5 left. Into 6 right to the crest, 50, brake, caution, bridge, slight right, 50, turn, heavy right. Into late, 1 left, open half long, 40, 2 right, tightens, and square left, 120. Slowing, 5 left of the crest, 30, 1 left sharp, and square right, and 6 left, slowing, 70. Turn square left, 50. 5 right. 5 left of the crest, 60. Slowing, slight left, and turn 1 right, and slight right, 70. Late, 6 left of the crest, 4 right, tightens, to 3 left of the crest, into 4 right sharp, through junction 60. Slowing, 6 left of the crest, and 1 right, unseen, to 2 left, 40, slight left, 30. 6 right, slowing, 50, 4 left, 30, 5 right, short of the crest, 120. Crest, 90. Crest, 80. Jump, 100, slowing, caution, slight right to slight left, and turn, 1 right. 40, crest, 200. Crest, 80, turn square left. And crest, 70, slight left, slight right, 130. Long crest, slowing, 100. Turn square left, LC. Into crest, and 1 right, and 4 left, 30. 4 right short, over crest, 30. 1 left sharp, into 3 right short. And 4 right, to 4 left, 80. 6 left, slowing, 50, late 3 right, half long, 50, 3 left, opens, tightens 4 for crest, 40, turn, 1 right, for crest, narrows, 6 right, into bridge, and 4 left, keep in, into 6 right, cut, into slight left, 140, slowing, crest, so 1 right, long, 40, crest, 40, 3 left, half long, tightens, hard crest, 30, turn, square right. Got 50. Jump 160. Caution, crest, turn square right. 140. Slowing crest, 50, turn square left. 150. Crest, 140. Caution, slowing, 6 left of a jump to 5 right. 1, turn square right short. 90, left of the crest, slowing, 50. Turn square left, late. 50, slight left to slight right, half long. Slowly, and left of the crest, and turn acute heavy right. 50, unseen, 3 left, tightens. 40, 4 left, 6 right of crest, slowing, 40, square right short, to 4 left, tightens, to 3 right short, 60. 4 left, half long, opens, and tightens, to 1 right short, 50, square left, and slight left, to 3 right short, slowing, and 5 left, into 1 right, opens, 40, 2 left sharp, into slight right, 80, 6 left at crest, to 6 right, cut, 90, caution, jump, over bridge, 40, left of a crest, and 20, turn, 1 left, cut, 70, crest, 30, slowly, slight left of crest, tightens, 40, slight right, into crest, 30, square right short, 110, crest, slowing, 100, left entry chicane, 150, turn square left, into crest, 200, big crest, 100, right of the crest, 120, slowing, 6 left, into late 3 right, 40, 6 left, cut, to slight right, slowing, to crest, 4 left, half long, slowing, 90, right, tightens, 4 left short, 50, slight right, 40, 2 left, cut, 40, late, 3 right, tightens, keep in, 4 left short, to sudden, 3 right, into slight left, 1 left of the crest, 40, crest, 70, square right, 40, slight right to crest, caution, 50, left of the crest, into turn, heavy left, 80, 6 right, very long, 40, 4 left short, keep in, to left of the big crest, to slight right, 80, slowing, 6 left, 30, 3 right short, to 3 left short, 70, 4 right, tightens of the crest, to 4 left, half long, 6 left, cut, 30. 2 right, 60. Late 5 left, for crest, 60. 3 right, opens, half long, tightens. 40, right of crest. And 6 left, half long, tightens 4, pass junction, 50. Slowing, crest, to turn, 1 right, 30, late 5 right, tightens at the crest. Right of crest, into 2 left, through dip, opens, and right of crest. And 4 left, half long, tightens, 40. Slight right, 80. 5 right sharp for crest, to slight left, 90. 6 right for the crest, slowing, 100. 1 right short, small right, 30. 4 right into 4 left, 40. Slowing, slight right. Turn square left. 40, slight left, 70, crest, 50. 5 left short, to 6 right, into bump, and 4 left short, into 6 right, 40, 1 right, to 4 left, late 4 right. Into turn, Q10 left. 40, low crest, 110. Turn 2 right, sharp, 180. Slight left of crest, 150. Slowing crest, to late 3 left, 40. 6 right to crest, tightens 4, open to crest, 30. 5 left, 40. 6 right, half long. Tightens 4 to 4 left, 60. Caution, square left to slight right, 50. 6 right. Into crest, to slight left, tightens 3, opens, 50. 3 right, tightens, 120. 1 left, tightens, into right of the crest, 40, 6 left, keep in. Into crest, 230. 6 left of crest, slowing, 70, turn, 1 right. And late, 3 right, the crest, 70. 6 left of the crest, slowing, 40. 2 left, opens 5, 30, water splash. Into 6 left of the crest, very long, to slight right, 50. 4 right short, 50. 3 right, tightens, to crest. Solid 2 left, unseen, opens, 50. Water splash, to 3 left, 50. 4 right, keep in. To 5 left short, 100. 4 right, opens, half long, 60. Turn 1 right to the crest, narrows, to the left of the crest, 40. 5 left, opens, half long, 40. Unseen, 4 right, opens, 120. Slight left, slowing, 130. Turn hairpin left. 60, slight right, slowing. slight left into 4 right on the crest, tightens into 4 left, and turn Q10 in right. And 6 right, to 2 left sharp, cut to 4 right, and 6 left, and 5 right, 30. Turn hairpin left. 50, small rest, 40. Turn the Q10 in right. 90, 6 right, long, keep in. And crest, slowing to 6 left, tightens 5. Into crest, sudden, 1 right, opens, caution, into crest, turn the Q10 in left.
frené con... Ah, pensé que no.
Hello, I'm Molly Pettit and welcome to the final round of the FIA World Rally Championship. It's almost time for the crews to get underway here at the fabulous Vodafone Rally de Portugal. The technical gravel stages here have seen a great deal of spectacle over the years, and I'm sure this edition will keep that tradition alive. So, the weather then. Looking at the forecast, it seems rain may be a defining factor for this rally. The wet weather may make things a bit trickier for the crews, as grip on this surface could be hard to find. And now to the standings. It's a new start to the championship here, and every team will be very aware that if they can perform today, they can cement a solid base to build on the rest of the season.
Towards the end of the 19th century, physics was flourishing. The principles of thermodynamics had helped to kickstart the Industrial Revolution, and Faraday had recently discovered how to generate electricity. Furthermore, James Clerk Maxwell's grand unification of electricity and magnetism had led to the remarkable realization that light was an electromagnetic wave. Spurred on by the power and reach of these new theories, physicists began using them to address some of the big unsolved problems of the day. One such problem involved explaining how hot objects emit light. It was well known that if you heat a lump of metal, it will first glow dull red, then orangey red, then yellow, and eventually bluey white at the same time as getting brighter. Physicists wanted to explain how the intensity or brightness of the emitted radiation related to the wavelength or colour. They realised that this would involve understanding how matter, the lump of metal, interacts with radiation, the light emitted, at a fundamental level. However, when Maxwell's theory was used in conjunction with classical thermodynamics to calculate the emission profile of a hot object, it predicted that all such objects should be emitting an infinite amount of energy at small wavelengths or high frequencies. Because high-frequency light was dubbed ultraviolet light, and because this prediction was clearly problematic, this issue became known as the ultraviolet catastrophe. It represented a complete failure of classical physics, and it was in attempting to solve this problem that Max Planck was forced to introduce the revolutionary concept of energy quantization, the idea that energy is transferred discretely in chunks rather than continuously. After Planck's work on this topic, the world would never be the same again. In order to properly understand Planck's solution to the problem and why this represents such an important turning point in the history of science, we first need to understand the cause of the problem. And to understand the cause, we need to start with some basics. When you shine light on an object, some of it may be reflected, some of it may be transmitted, and some of it may be absorbed. Darker objects tend to absorb more of the light incident upon them and reflect less than lighter objects, which is why they appear dark in the first place, but also why they tend to heat up more quickly. Think about how black surfaces heat up in the summer compared with white surfaces. An object that absorbs all of the light incident upon it is referred to by physicists as a black body, for obvious reasons. If the temperature of a black body is less than the temperature of the environment in which it is placed, then it will continue to absorb energy from the environment until it has reached the same temperature, at which stage it is said to be in thermal equilibrium. If, however, the black body has a temperature which is higher than its surroundings, then it will radiate energy away until it has lowered its temperature sufficiently to reach thermal equilibrium. Therefore, a black body is not only a perfect absorber of radiation, but also a perfect emitter of radiation. Furthermore, experiment shows that the wavelength intensity profile of a black body has a universal character, which does not depend on the shape or composition of the black body, but only on its temperature. It is this relative simplicity that makes the black body highly appealing to physicists and the logical starting point for any inquiry into the radiation properties of hot objects. An example of a real black body studied by physicists is called the Jeans cube, named after the physicist Sir James Jeans, who, along with Lord Rayleigh, provided one of the first attempts to explain the radiation emitted from a black body. A Jeans cube can be thought of as a cubic metallic box with a very small hole in one of the sides. Radiation incident upon the hole from the outside will enter the cube and reflect back and forth off the walls until it is absorbed. Given that the hole is very small, only a tiny fraction of the radiation inside the cube will ever escape back through the hole. Therefore, from the hole's perspective, essentially all radiation incident upon it will be absorbed, and therefore the hole acts like a black body. We can also consider the reverse process, in which the walls of the cube are uniformly heated to some temperature, such that the walls start emitting radiation and filling the cube. Given that a small fraction of this radiation will then escape through the hole, we see that the hole acts like an emitter of radiation. Since we've already established from the absorption
Go.
factors
Left of a crest,
that behaves
120.
as if it is a black body, it
Slowing,
follows that the
slight
radiation
left,
emitted by
50
the hull
left of a
should
crest,
have the
onto
intensity
tarmac,
profile.
and 5 right, long, tightens.
Furthermore, since the hull is simply sampling the thermal radiation inside
And
the
crest,
cube,
and lead
it is
3
clear that
left,
the radiation
10.
inside the cube should also have the wavelength intensity
6 left,
of the black
70.
body. Groundbreaking
Slowing,
experimental
left of a crest, 50.
idealized black bodies
Lead
which
3
carry
left,
high
long,
octane
tightens.
and earn spring shine. And these experiments
40,
provide
slight
valuable
right,
data
tightens 4,
theoretical physicists
very long,
to
keep in
investigate.
70.
The experimental work involved measuring the spectral radiance of the black body as a function of wavelength.
Lead 3 left,
This
half
resulted in
long,
characteristic
60.
curves which varied with temperature.
2 right,
The lower
don't
the
cut.
temperature, the flatter the curve. The spectral radiance
80
is defined
crest,
as
60.
the energy per second
6
per
right,
unit area
tightens.
per
Swap
unit
jump,
wavelength,
130.
which is simply the intensity per unit wavelength.
Finish.
Since intensity is defined as power per unit area, it follows that the units of spectral radiance are watts per cubic meter. To find the intensity from one of these graphs, you simply have to
Thank you. Thank you. Thank you. Thanks a lot. Thank you, James. Thank you, all of you, for coming on a Saturday night. I'm sure you had nothing else to do on a Saturday night in London. So thank you for coming. I'd like to start by thanking the whole Royal Institution and Princeton University Press, everyone here from Dan to Rachel's to Stephen to James, Josh, and everybody. So thank you very much. I'm Claudia Duran. I'm a professor of theoretical physics at Imperial College London, and there I study the secrets of gravity. So as you can see, I've done really good progress in the past few years because I found a secret to mysteries to float in midair, as you can see in the picture. But the reality is most of the time, my own experience with gravity looks much more like this. And I can show that picture over and over again, and it's quite universal how people enjoy seeing me fall down, so that's good to see. But one of the secrets I'll share with you tonight is that deep down, I do think that gravity could have its own sense of humor. And it's a little bit like my own sense of humor. It may take a few billions of years for you to really appreciate it, so just be patient. Okay, so now that we have establish what it looks like or what it feels like to witness someone else experiencing gravity, let me ask you a slightly more personal question. What does gravity really feels like to you? And you may think of gravity as being associated to the pain you feel upon impact, upon a fall, but that in itself has got nothing to do with gravity. The pain you feel upon impact is related to the contact forces between solid objects, and particularly to the electromagnetic atomic bond within the cells of a body and that of the ground, and actually to Pauli's exclusion principle that prevents,
Starts
for
left of a
instance,
crest,
two electrons
20. Good luck.
from sharing the same state at the same time. And so the cells of a body and the atoms of the ground have to adapt for each other upon impact. That on itself has got nothing to do with gravity. So to really experience gravity much more truly, we should really extract ourselves from all the other forces, for all the other phenomena. And then somehow a lot of my friends often tell me that I should just go skydiving, ideally without a parachute. I don't know what they mean by that. So that I can really experience this feeling of
5,
freedom.
4,
But I'm not
3,
entirely free there.
2,
I'm not entirely in free fall.
Go. Left
Because
of
of
a
the
crest,
friction of the air
120.
that still pushes against the front of
Slight
my body.
left, 50.
And I feel
Left of a
I
crest,
feel this
onto
push,
tarmac,
this
and
pressure.
5 right, long, tightens.
On the rest of my body, and this is me actually going
crest,
skydiving
and
without a
3 left,
parachute.
110.
And I can tell you do feel that, particularly on the next day.
6 left,
But on the rest of your
70.
body, you don't feel anything at all.
Slowing,
Even
left of a
though
crest,
gravity is
50.
clearly acting on you.
Link 3 left, long, tightens.
But you don't feel anything at all because gravity
40, slight
is acting
right,
on
tightens
every
4,
cell of
very
the
long,
body
keep in 70.
in exactly the same way. And so they're not pushed or torn apart. In fact, there's no single cell or
3
taste
left,
bud
half
in
long,
your body that
60.
can ever feel or taste or
right,
smell
don't cut.
or hear gravity. If you're experiencing
80
gravity
crest, 60.
in outer space, for instance,
6
orbiting
right,
the Earth,
tightens of a
you
small
will
jump,
be
30.
falling so freely that you don't feel
Slight
anything.
left, long, to
And
right
yet,
of a crest,
you're falling,
70,
you're
slowing,
experiencing gravity. But you're not
8,
feeling
3
anything
left,
at all.
half long,
Because
80.
every
6
particle
left of crest,
in
half
every
long, 50.
atom, in every molecule, in every cell of your body, as well as all the
3
air in your
right, opens
spacesuit,
half long,
is experiencing gravity
crest,
in exactly
40.
the same way. There's something
8,
very
3 right,
universal.
of a crest,
Actually,
220.
we call this the equivalence principle, which tells you that gravity acts on everything and everyone in the same way. And this equivalence principle was already postulated by Galileo at the end of the 16th century. And it was, for instance, one of the experiments that was first made to see, well, not the first one, but one visual way to see this equivalence principle was done during the Apollo mission on the moon by astronaut Mark Scott, as you can see here. Not because gravity is any different on the moon, but because there's no atmosphere,
8, 4
there's
left,
no
slow,
friction.
70, crest, 60.
So when I
square
play,
right,
you'll see
onto
that
gravel,
astronaut Mark Scott is going to drop
70,
on one
right of the
hand
crest,
a feather,
60.
on the other one a hammer. And hopefully, they will hit the ground at exactly the same time, proving
Right
that
of the
gravity
crest,
acts on the
slowing,
object
60,
exactly the same.
crest, 102 left, 70. 6 right of the jump, 30.
He works! How about that? Galileo was correct. This is the equivalence principle. So I spoke with the Royal Institution when I was giving a talk here, and we discussed about how to prove the equivalence principle here. And I said, well, really, we should all go on the moon and experience that. And somehow they didn't want us to do that. So instead, thanks to Rachel, we have a really amazing experiment here, which is a tube. It's actually a tube, a normal tube. And Rachel has very nicely sucked all of the air out of the tube. And it's filled with some pieces of paper and a coin. Because there's no friction from the air, you can see that the paper and the coin fall in exactly the same rate. Even though their mass is clearly different, the shape, the color, everything else is clearly different. And yet, if you extract yourself from as many of the other external forces as you can, you see that these different masses experience gravity exactly. So this is what we call the equivalence principle, and it's really telling you that there's a level of universality in how we experience gravity, how we interact through gravity. And this is really what pushed Einstein to understand that there must be something much more fundamental about gravity. If everyone throughout the universe experiences gravity in the same way, and you can be something as heavy as a black hole or whatever, quite as heavy, or as light as a feather, or even as light as light itself, and you will still be experiencing gravity. It means that there must be something quite deep in this way we understand gravity. It can't just be about two masses interacting with one another. It has to be encoded in something deeper than us. It has to be encoded in the very fabric of space. And now we understand, thanks to Einstein's theory of generality, that masses, like you and the Earth and the Sun, curves the very structure of space-time around themselves. That's how we're experiencing gravity. We all feel space-time. We all feel this curvature. That's how we feel the gravitational attraction. The larger the mass, and the bigger the curvature, the larger the gravitation. Now, throughout the universe, everyone is connected through this very fabric of space-time. So everyone and everything is connected through gravitation. We are connected through this gravitation. Actually, the very notion of curvature, and hence the very notion of gravity, relies on connecting different parts of one another. If you want
Three
to
right,
draw an
one
analogy between the curvature of space-time with the curvature
Six left of the
of a
crest.
surface, it's easier for us to
And 3
represent.
right, onto tarmac,
So you can
30,
think of the
6 left of the
curvature of the
crest, to
surface
6
of
right,
Earth, or
40.
this very beautiful surface here, which is curved. And we can tile this curved surface with
Turn 3
tiles
left,
which are
over
each
crest,
one of
90.
them individually completely
Caution,
flat.
6 right, long,
Completely
tightens.
flat, each one of them. And it's connecting, it is in connecting those flat tiles with one another that the curvature of the surface
Into slight left of the crest,
unfolds.
70. 3
And in
left
here,
short, cut, 40.
I've drawn a
6
straight
left,
line
slowing, 30, turn,
connecting
1
those
left,
tiles.
60.
It's a completely straight line. And when they are on this curved
30.
surface, this straight line may appear a little bit
Crest,
funny
onto cold.
or curved.
Late 4 right,
It is
half
just
long,
the way a
50.
straight line looks
Late 4
like
left,
in a curved
tightens,
space.
40.
Adapting to the curvature of the space or the space line.
Crest, slowing, 80.
And that's why, for
Turn,
instance,
square
the
right of
orbit
the crest,
of the
onto
planets
gravel.
around the Sun may
30,
look like
5
they're having
left,
some
5
curved
right,
ellipses
over bump,
around
60.
the Sun. But actually, these are just straight lines in the curved space-time.
Left of
They
the
are
crest,
adapting for the
slowing,
curvature in
100.
which they live in.
2 right short, 70.
Now for me,
6 right,
this experience is
tightens
very
of the crest.
tangible because throughout my life, I have been
Into
moving
crest,
from one
caution, sudden,
to
1
another.
left, half long
Very
opens,
conscious
6
at every
left of
step
the
I
crest,
had to connect
50.
between these different points. Switzerland,
5 right, past junction, 60. Left of the crest, into slight
France,
right, 50.
Asia, to Canada,
Late 3 left, and 6 right of the crest, 30.
to US.
3 right, opens,
And every
into
time,
crest,
as I left
6
behind
left of the crest.
everything and everyone
Into
that
slight
made me
right.
who I was,
to late 3 left, tightens,
it became clear
30.
that
Long
my
crest,
entire
20.
existence, but also all of your entire existences,
6
and nothing
left,
other
60,
than
slowing,
patchwork
5 left of the
of
crest,
events
half long
in
tightens,
space.
and 2 right,
That's up
100.
to me, that's for all of us, to
Slight
connect between
left,
them.
slowing, 50.
In fact, there's never such a thing
Crest,
as a
40,
twisted
turn,
lighthouse
square
in a
left,
straightforward
to
world.
4 right, to
Rather,
5
we're
left
all
of the crest.
experiencing straight trajectories, adapting for the complexity for the world in which we
And
live.
4 left, tightens,
And throughout
50.
those journeys,
1 right,
the whole sky and nature at the more fundamental level is always there with
30,
us,
slow.
a little bit like family. So whether we know it or not,
right,
and I know
half
you do
long,
know it,
30, 6
but I
left of the
think that's
crest,
why we all
tightens, 3.
inhabit it, with a desire to understand nature at the more
Into
fundamental
crest,
level.
80.
So let's do that. Let's
left sharp,
understand the
50.
fundamental forces of nature.
Turn,
And let's
1 left
start
short,
with the one we
widens,
understand
onto
the best,
tarmac, to
the
slight
electric
right,
and magnetic
60,
forces.
bridge,
In
50.
this very theatre, some 225 years
6
ago,
right, half long, 80.
some of those experiments
4
with
left,
electric
half long,
magnetism
don't cut.
were done by Faraday himself.
60.
These, one of the first I
6
realized
right,
that
half long,
the electric and
tightens,
magnetic forces are
slowing,
not two
70.
disconnected phenomena.
Turn, late
They are actually
hairpin
two
right,
different
onto
manifestations
gravel.
of the very same phenomenon.
100,
We
6
know
left of the
that
crest,
magnetic
very long.
phenomenon has helped us as a civilization to travel the world for thousands of
Tightens
years.
4.
But that's actually nothing as compared
Into
to
3
the
right.
impact that
Into crest,
electric force has
5
had
left,
on
50.
health, as we all know.
3 left of the
This
crest,
is something
60.
that we've done last week because there's a small
Long
chance
crest.
of having a heart attack when you do it. So I'll ask a volunteer to do that
Into
right
left
here,
of the
right now
crest,
first.
and 1 left short, 30.
No one? No one?
Late
We
hairpin
have
left.
a little
And
volunteer
2
here.
right, opens.
We can always count on Barbie, so thank you, Barbie. She's gonna show us how
And 1
the
left,
force
don't
acts.
cut.
And one thing, when I switch it
And
on,
3
there's a
right,
small
half
chance
long,
that
120,
none of us will have a heart
slowing.
attack apart from Barbie, thankfully. There's a small chance that everything will go dark.
Late, square
This
right,
is to show
half
that
long,
without
30,
electric force,
3
gravity
left, don't
wins.
cut. To 5 right of the crest.
But as I'll switch on, you'll see that
And slight
the electric
left,
force is so much
30.
stronger
6 left,
than the force of gravity.
to 4 right of the crest.
You have to
to square
apologize.
left short, and slight right, to
I'm so
70.
sorry to Barbie. She's a little bit burnt. That's because she's been on a
fight with Oppenheimer earlier this weekend. She won!
Right
So
to
that's
crest,
fine.
40.
There's an order in the world.
Into 6
So
left.
when I put it on, you'll
Into
see her
crest.
hair will go up. And what I like
3
you to
left,
see,
40.
if you really realize, is how just the
6
transfer
right.
of a few electrons in her hair,
Titus 3.
there is
30.
some electromagnetic
Left,
repulsion that
30.
compensate the gravitational attraction from the Earth. And just
2
realize
right. Into
how weak
crest,
the gravitational
90.
forces. Just a few electrons on her hair can compensate the whole gravitational attraction from
Into 6
the
right
Earth.
of a
This is
crest.
remarkable.
And
So
left
let's
of
see
a
if it
crest.
works.
Slowing, 80.
Just walk away.
Left. And slight right. Tightens 2. And 2 left. And turn heavy right.
The screen switching off, and my audio is off as well. Just
50.
show the effect.
Left
One
of
thing
a
you can
crest.
notice
80.
here is that there's sparks coming on. There are sparks of light.
For finish.
The
To stop.
sparks. Let's see if things go back on again.
Okay.
I know. But it's intentional. It's to show you that related to a discharge of electricity, there's a production of light because electric charges are being accelerated through this discharge of electricity. And actually, Faraday himself was one of the first ones to postulate a connection between light and some electromagnetic vibrations. Nowadays, we understand that when we accelerate electric charges, we produce an electromagnetic wave. This is just a very fancy way to say we produce light. Light is actually the messenger for the electromagnetic wave.
Start left of a crest.
The electron,
20.
they
Good luck.
communicate some sort their electromagnetic repulsion against each other through a messenger, which we can think of it as light. We know there's lightning when there's a quick discharge of electric field, for instance, during a storm. And we're using that in our everyday technology now, of course. We're using this in the bulbs, which rely on electron being accelerated back and forth to produce light. Or we rely on that for telecommunication in antennas, which is also acceleration of
5,
electrons that
4,
produce radio
3,
waves
2,
for telecommunication.
Go.
Radio waves
Left
are
of a
nothing
crest.
other than
20.
electromagnetic waves at
Slowing.
magnetic
Slight
frequency.
left. 50. Left of a
We're
crest.
using that
Onto
in our
tarmac. And 5 right.
So why am I talking
Tightens.
about all this?
And crest.
Really,
Lead
we are
3
here
left.
to understand the
10.
secrets of gravity. And I said that gravity maybe is a manifestation
6
of the
left,
curvature of
70.
space-time, maybe it's not the force. You've probably
Slowing
heard that
left of
a
a
lot of
crest.
times, that
50.
gravity is not a force.
Late
And yet
3
I'm standing
left.
here
Tightens.
and I'm talking about a force.
40. Slight right.
Because
Tightens
deep
4.
down,
Very
gravity
long.
is
Keep in
a
70.
force. Deep down, gravity, even though it is a manifestation of the curvature of space-time, it has
Late
hidden
3
in it
left.
a
Half
force in
of
itself.
60.
And it can be described in exactly
2
the
right.
same way
Don't cut.
as the electromagnetic force. In the same way as when I
80
take
crest,
electric charges
60.
and accelerate them with one another,
6 right.
I
Tightens.
produce
Of a
some
small jump.
electromagnetic field,
30.
which are called light.
Slight left.
Now, when I take
right of a
masses,
crest,
which is my
70,
analog to
slowing.
the electric charges for gravity,
Late
when I
3
take
left,
masses and
half
accelerate
80.
with respect to one another,
6 left
I
of crest,
produce
half
gravitational
50.
waves, which I personally like to call the light, but that's not the same.
3 right. Opens half long.
Now, when I shake my hands like this, I do
crest,
produce
40.
gravitational waves.
Late 3 right. For crest. 220.
Don't say yes. Please. The intensity of those gravitational waves when I do that is so small that we're never gonna
Slowing.
detect.
70.
Ever.
Crest. 60.
To produce
Turn
gravitational
square
waves with
right onto
sufficiently
gravel.
high intensity, magnitude to be observable, we
70
need huge
right of the crest,
objects,
160.
very massive objects, and accelerated very close to one another. So thank you for not saying yes. So that you feel my gravitational wave.
Right of the crest. Slowing. 60.
So for instance,
Crest.
two
Sudden
stars
2
and two
left.
black holes
70.
about
6
to
right
merge.
of the jump. 30.
When they are about to merge, they produce gravitational waves, and those gravitational
Slight
waves,
left,
once
30,
produced, they
bump,
travel through
50,
space and time over
6
millions of
left,
years
70.
to reach us
Late
here
4
on
right.
Earth,
Tightens
and we can
3
detect
over
them
bumps.
through
Don't cut.
instruments
And 2 left.
which measure
50.
how space and time
5
get
left of crest.
distorted as gravitational waves pass through. So
Into
this
slight right.
instrument, we call them
Into crest.
interferometer,
Into 6
and
left.
their role
70.
is to
Late
measure
3 left.
distortion in in space in
Into
various
crest.
directions.
And right to the
As
crest,
gravitational
40.
waves pass through,
One right,
we can
half
recognize a
left.
signal, as you can probably see on the top left.
Into slight left of
You
the
may
crest.
recognize this signal. This is the first signal of
slight right,
gravitational waves
70.
ever observed here on Earth in September
Slowly
2015.
dip to 3 left
And
of
the
the crest.
announcement of that was on
Tightens,
February
30,
11,
square right,
26.
and 6 left.
On the day of the announcement, you could pick up any newspaper throughout the planet on any language that you want, and the headlines
Into
would
slight
read,
right,
Einstein
30,
was right.
6 left over bump, into jump,
And
50
so you'll be
crest,
forgiven
4
for
right,
thinking
don't
that
cut,
the
into
detection of
crest, into 3
gravitational
left,
waves
through
may
dip,
have been about proving
and right to the
Einstein.
crest.
But that's never the case. We don't do
5 left
science
of
to
crest.
prove someone right or
And
wrong.
right to the crest,
We do
4
science
left,
to discover
through dip,
something new.
tightens,
We do science to push the barriers of
4 right to
understanding.
the crest,
And
half long,
according to
30,
Einstein's theory of general relativity
4
itself,
left of the crest,
there's still
into
much
slight
more to
right,
uncover.
50, slowing, crest,
And that's because
60,
Einstein's theory of general
late hairpin
relativity
right,
doesn't only predict gravitational waves,
and
and
turn
the Big
hairpin
Bang,
left,
black holes,
and 6
so
left.
many other amazing things. Actually, the very best thing I would say that Einstein's
70,
theory of general relativity
left of the
has
crest,
is its own failure.
water splash,
And that's undoubtedly the best feature that a theory can ever have.
slowly,
Because
slight
it not only
left,
tells you where you are
into right of the crest,
and how to make
40,
predictions
4 left
and
short,
compare
into
with
2
them
right
with
sharp,
observations.
40,
It
6
also
left,
tells you
upwards
where to
long,
look for new discoveries. Now, to understand why
Tightens of the
Einstein's
crest.
theory of general
into
relativity
5
does
right,
indeed predict
slowing,
its own
70,
failure,
hairpin left,
it's useful to go back once again to the other fundamental forces
30,
of nature.
right short, 40,
And you may think of there being
One
many
right to
different
crest, 80.
forces of nature. But many of the forces that we experience in our everyday life are more contact
3
forces,
left sharp,
which some of them are
and slight
related
right,
to
opens the crest,
Pauli's exclusion
50,
principle, and some of them are related to much more
6
fundamental
left,
forces of nature.
tightens, 50,
Actually, in terms of fundamental
3
forces of
right,
nature, there's only
100.
4 of them that we know of so far. There's electric and magnetic force
6 left
put
to
together
crest.
as one, as
and
electromagnetism,
3 right, onto
Then there's the
tarmac,
weak force,
30, 6 left of the
which is
crest, into
responsible
6
in
right,
some sense
40,
for the structure within the atoms. There is the strong force, which is responsible for the cohesion of
turn
the
3 left,
quarks
for crest,
within the
90,
protons and neutrons inside the
caution, 6
nuclei
right,
of the
long
atoms.
tightens,
And then there is the fourth one, is the
into slight
gravitational
left of the
force.
crest, 70,
And one thing
3 left
remarkable
short,
about all
cut,
of those
40,
fundamental forces of nature
6 left,
is that we
slowing,
think they
30,
can be
turn, 1
unified
left,
into
60,
one theory of everything. We
4
already
right,
know
30,
that the electric and magnetic forces are not disconnected, they're
long crest,
unified into
onto
one
columns,
frame.
late 4
And I
right,
mentioned
half
later, the
long,
weak force
50,
can also be
late 4
unified
left,
with
tightens,
electromagnetism
40,
into an electroweak theory. And we do believe that this continues and continues. If we go back to electromagnetism,
crest,
while I
slowing, 80,
described it as being having a messenger,
turn, square
which
right
is
of the
like
crest,
the
onto gravel,
electromagnetic wave, at a
30,
more
5
fundamental
left,
level,
5 right,
light
over bump,
can be
6,
described as a wave, but
left of the
also
crest,
as a
slowing,
fundamental
100,
particle which we call
2
the
right
photon.
short, 70,
In
6
practice,
right,
what this means
tightens of the
is
crest,
if I take light of a particular color
into
or
crest,
frequency
caution, sudden
and
1
reduce
left,
its
half long,
intensity as
opens,
much as I
6 left
can,
of crest,
I'll
50,
see that it's carried by
5 right,
finite
last junction,
discrete
60,
quanta
left of the crest,
of
to
energy,
slight right,
which
50,
we call the photon.
late 3
There'll
left,
be one
6 right
photon,
of the crest,
one
30,
amount of
3
energy,
right,
or
opens,
2 photons, a double
into
of
crest,
energy, but
and 6
never
left of the
anything
crest,
in between, no matter how much I try to
to
adjust
slight
it.
right, to late 3 left,
In fact,
tightens,
individual
30,
photons can be
crest,
emitted or absorbed
20,
when electrons change energy levels around the
6 left, 60, slowing, 5 left of the
Now,
crest,
the weak
half long
force is
tightens,
also a fundamental
and 2
force
right,
and can be
100,
unified with the electromagnetic force
slight
into
left,
an
slowing,
electroweak
50,
theory. This is known thanks to the work of
crest,
Lancia,
40,
Salam,
turn
and
square
Monte.
left, to 4 right, into 5
The
left of
weak
the crest,
force also has a carrier which transmits this weak force, which we call the W and the Z
left,
bosons.
tightens,
Those are
50,
also fundamental
right.
particles, which we can detect absorb and
30, slowing.
the weak force is actually extremely important.
Right,
We wouldn't be
half long,
there
30,
without
6 left of the crest,
it's
tightens
responsible
3.
for fusion. It has some medical applications. Some of
Into
you may
crest,
have gone through a
80.
PET scan, which relies
3
on
left
this
sharp,
weak force.
50.
And on the W and the zeros.
Turn, left short,
But we may not be quite as familiar with this weak
slight
force
right,
because
60.
the weak force is
Bridge, 50.
weak. It's weak. It's very weak.
6 right,
At least there's one
half long,
concept.
80.
It's quite easy. It's weak here. And the reason it is weak
half long,
is
don't
because the particles that carry it, the W
60.
and the Z bosons,
6
are
right, half
massive
long, tightens,
particles
slowing,
in the sense that they
70.
have a mass, which
Turn,
means that they're much
late,
harder
hairpin
to
right,
excite.
onto gravel.
And nowadays we understand very well how the Higgs mechanism is responsible for giving a mass to the W and the Z boson. I'll explain what I mean by that. And is responsible for weakening
3 right,
the range
into
of
crest,
the weak
into
force,
5
making the
left,
weak
50.
force weak. Electromagnetism, we say, has an
60.
infinite reach. And first of all, we can have two electric charges quite far away from one another.
Don't cut
And
to the left
technically,
of the
they will
crest.
still
Left short,
radiate
30.
a small
Late
electric,
hairpin left.
electromagnetic force with one another.
And 2 right,
But for the weak
opens.
force, we know that it has a finite range. It only operates on subatomic scales.
Left, don't cut.
And beyond that, it switches
Up
up.
3 right,
So on bigger
half
scales, we don't
20,
experience it. We don't
slowing.
experience the weak force. And we understand how the Higgs mechanism is responsible
Late,
for
square right,
switching
half long,
this weak
30,
force
3
up
left, don't cut.
on larger
5 right
distances.
of the crest.
very slowly. I'm
And
sure you all
side
know
left,
that the
30.
Higgs goes away.
6 left.
Very sorry.
Into 4
And I
right
thought,
to the crest.
as a nice
To square
gesture,
left short.
I will
And side
add a
right,
picture of him
70.
when he came to visit our physics department a few years ago. And I think this is quite symbolic
5 right
of
to the
showing
crest,
how
40.
interactions
2 right.
between Higgs
Into
himself
6 left.
and people around
Into
him
crest.
has an impact on
And late
people
3
around.
left, 40.
Because this is precisely how the Higgs mechanism works.
6 right.
In reality,
Tightens
many
3,
other people
30.
and scientists were included in the discovery of the Higgs
30.
mechanism itself. But I call it the Higgs mechanism.
2 right to crest, 90.
Actually, Higgs mechanism has really allowed us to
Left.
understand
To 6
much more
right of the crest.
deeply
And
what
left
it
of the
means
crest,
to have
slowly,
empty space.
80.
It tells us something very profound
left.
about our
And side
understanding
right.
of empty
Tightens
space.
2. And
So to
2
understand
left.
what we mean by empty space, we're going to take this room
Turn, hairpin right.
and we're going to create a perfect vacuum here. So in a second,
50.
I'm going to ask you to all
Left
leave,
of the
please.
crest, 80.
And please take all the furniture along with you. All the air in this room, take it along with you. I'm a theorist, so I can tell you, but I can't
Okay.
do myself.
That's a
We're going to
10-minute,
create the perfect vacuum.
29.6.
When you go out, close the door. And what we're going to do is make sure we shield the whole room with a few kilometers wide walls so that no energy, no light, no cosmic ray from the outside can enter the room. So we will have created the perfect vacuum in this room. We may well win the Nobel Prize for how beautiful a vacuum this is. And yet, this vacuum is never really empty. It's filled with a vacuum bath, which is quantum fluctuations from all of the particles that we know of, including that of the Higgs. I'll call this the vacuum bath or the Higgs bath. And we know the detection of the Higgs and the understanding of the Higgs mechanism is a proof that this Higgs bath has an effect on other particles. We understand that the Higgs mechanism works as its interactions with the other particles. Light or massless particles, like the photon, don't interact very much with this bath. And so they're not affected in the dynamics. More massive particles, like the W and the Z boson, interact very strongly with the bath, and they are affected in the range of the dynamics. This is how the Higgs mechanism works, and that's how this bath, the Higgs bath, weakens the range of the weak force, weakens the dynamics of the W and the Z boson. But now we know from the equivalence principle that everything is connected to gravity. So this Higgs bath, for instance, is not innocent. it should have an effect on gravity. So let's go back to gravity once again. So just like we described the electromagnetic phenomenon as a force which had a messenger being light, but at a more fundamental level, light is carried by a particle which we call the photon. All of this is true for gravity. Deep down, gravity is still a force, even though it can manifest itself through the curvature of space-time. And just like the messenger for gravity or gravitational waves, if we took gravitational waves, it's very hard to detect them, so we can't really just take them like that. But if we were able to take gravitational waves and reduce their intensity as much as we could, we would see that they are carried by finite discrete quanta of energy, which we call the graviton. According to Einstein's theory of general relativity, the graviton is a massless particle, like the photon. But we'll see that this is not necessarily the case. In principle, individual graviton could be emitted or absorbed when electrons change energy levels around the atoms. But the probability for this to happen is extremely weak. And observing this will be extremely hard because gravity, as we've seen, is the weakest force there is, which means that we interact very weakly with individual gravity. So we've seen one here. That's my graviton. That's been made by my student Alicia. And now that we have a new toy in town, the graviton, what we're going to do is to explore it and understand how it works. So I don't know about you, but at home, when we have a new toy, the first thing we do is we kick it and smash it and crash it to understand how it will behave. And so let's do that. And actually, this is exactly what has been done in any particle collider. In any particle collider, they take, this is the one at the LHC, the Large Hadron Collider, at CERN in Geneva, and in this case, they take protons and they smash them together to see how they will respond. And when this happens, sometimes the particles decide to transform themselves into some other particles. Sometimes they decide to do very different things. When we scatter particles, the precise outcome for one specific process is never certain. However, the probability of every single possible outcome can be computed with extreme precision compared with our observations, and it matches perfectly. We understand extremely well how the laws of quantum probability match our understanding of particle physics and our observation and experiments. Now I can try to do the same thing with gravity. Of course, I can't do it quite in practice, but as a thought experiment, I can ask myself, hypothetically, what would happen if I were to take, for instance, two gravitons and smash them together? And I can use our laws of quantum probability, and I can use Einstein's theory of general relativity to determine the probability of the outcome. And this probability of the outcome is very well understood, can be computed. It makes complete sense all the way up to the point where I'm trying to be too greedy and the energy transfer in the process reaches an upper limit, which we call the Planck scale. I'll indicate the Planck scale here as M for the Planck mass. This is a Planck energy scale. This energy scale is 15 orders of magnitude larger compared to what is currently being probed at the LHC. So that's a million billion times larger than the energy scale being probed at the LHC. So we're still a long way off from that. We don't need to worry. But what this tells us is that there's an upper limit up to when I can use Einstein's theory of general relativity to make predictions. And beyond that, the theory itself tells us nonsense. It tells us we have more than 100% probability of something to happen. Sometimes we have a negative probability of something else to happen. This tells us that we can no longer use the theory itself to make predictions at those energy scales. Now, as a theorist, I'm used to trading notion of energy with that of mass. This is what the famous E equals mc squared law tells us. You've probably all seen it. It's the most famous equation in the whole universe, possibly. It tells you that a notion of energy sometimes can be in the form of mass, but also mass sometimes can want to transfer energy. So there's a notion of high energy can correspond to a notion of large mass. But as we've seen, a large mass leads to a large curvature. And so what this tells us is that there are regions in the universe where the curvature is so high that the energy scale associated with it is close to the Planck scale, and we can no longer use Einstein's theory of general relativity to describe what happens in those places. Now, in the solar system, the energy scale associated with the curvature is always very small, even if you get very close to the sun. So we are safe there. It's all fine. We can use Einstein's theory of general relativity to make predictions, compare with the outcome. Whew, that's okay. To reach a curvature related to an energy scale which is close to the Planck scale, we need very large masses confined to very small regions of space. For instance, a black hole. And black holes are not just fragments of our imaginations. Black holes are unavoidable, and they have been observed. On your left, observation from the Keck observatories has been tracking the motion of stars at the center of a galaxy for a period of over 18 years, and you can see that they all seem to orbit an invisible mass at the center of a galaxy, which in fact has all the characteristics of being a black hole. And on the right is zooming towards the very same region at the center of a galaxy, now with the Event Horizon Telescope that measure radial light. So these are fake color, light at a particular frequency coming from behind that very same mass at the center of a galaxy. And we see that light has been bended by that huge mass at the center of a galaxy, and this is completely consistent with how we would expect a black hole to bend light around itself. Now, if you were to find yourself at the center of a galaxy, as we did over the weekend, this is not what you would see. You probably wouldn't see anything. These are fake colors. But what you would experience would probably be quite dramatic. As you get closer and closer to what we call this event horizon of the black hole, the horizon of the black hole, the gravitational attraction will become so large that you could try to run away from it. You wouldn't be as fast as the speed of light, and you wouldn't be able to escape. And once you enter the black hole, enter this horizon, there's no escape whatsoever, even if you were able to travel as fast as speed, no matter how much you try to rush yourself. As you go towards the black hole, you'll be squeezed along the transverse direction and pulled along the radial direction to the point that there'll likely be not much left of you by the time you cross the horizon. The experience may be a tiny little bit painful. And one way or another, by the time you enter the horizon, you'll likely be a little bit dead. However, as you go, I'm sure you'll be very relieved with the knowledge that Einstein's theory of general relativity is completely valid. This may not be a very safe place for us as human beings, but as a theoretical physicist, that's a perfectly safe territory. We're perfectly happy there. Gravity has been tested at those curvature scales, and is perfectly fine. So we can use Einstein's theory of general relativity inside the black hole to predict what will happen, even though we can't really go there. One thing that would happen is that the notion of space and time will switch with one another, and so I can't really discuss about the distance to the center of the black hole. I should really talk about the time scale to the center of the black hole. The distance, if I were to say it like that, is 11 million kilometers. That's about 30 times the distance between the Earth and the Moon. And in time scales, that's about 40 seconds. This is for the black hole at the center of a galaxy. Einstein's theory of general relativity will tell you that as you enter the black hole, you get pulled inexorably towards the center of the black hole, which is located in your future, in time in your future. And as you get pulled towards the center of the black hole, the curvature increases and increases. And it increases and increases all the way up to the point where it reaches, the energy associated with it reaches the Planck scale, by which point you can no longer use Einstein's theory of general relativity to trust what happens. So the beauty is that you can trust Einstein's theory of general relativity telling you that it will fail at that point. Precisely what happens there, and even if the notion of space and time makes sense, so even if the very question of what happens there, which precludes the notion of space and time in itself, makes sense, is unknown. All we know is that we need a better description for gravity and for the laws of nature to have a better appreciation of what happens there. Einstein's theory of general relativity has broken down, has failed us before you reach the center of the black hole. So this is a current understanding and description of gravity. We know that Einstein's theory of general relativity is an extremely good description, impeccable description, I would say, for the behavior of gravity on a huge variety of scales. It works well in the solar system, in a galaxy, on a cluster of galaxies, but there are regions, there does exist region in the universe where the curvature is so high that Einstein's theory of general relativity has broken down, and we need a better description to describe what happens in those regions of the universe. Precisely what it is, I don't know. I wish I could share that secret with you, but I don't know. It could be string theory, it could be quantum loop gravity, it could be causal set, it could be something yet entirely, I don't know. One of the challenges that we have at the moment is understanding how, with underlying framework which we don't know about, how can we make predictions for what we should observe today? This is very challenging, but this is some of the work that my collaborators and I, and a big part of the scientific community, are trying to do at the moment. However, what I'm even more interested in is to understand what happens at the other side of the spectrum. That's another secret of gravity I'd like to share with you today. So what I'd like to understand is, if gravity fails us on very high curvature scale, could it be that gravity also fails us on, or I should say Einstein's theory of general relativity also fails us on very small curvature scale? So to understand how to look at gravity in regions of the universe where the curvature is extremely small, what we should do is zoom to the largest possible scales in the universe. So we can zoom out of the solar system, zoom out of the galaxy, zoom out of a local cluster of galaxy, over distances that span over billions of kilometers. It would take us millions of light years, it would take us millions of years to get there if we were traveling at the speed of light. What we see on those distances is that clusters of galaxies are distributed along filament of dark matter, which are represented here in blue, but these are just fake colors. We can't see dark matter because light doesn't interact with dark matter, so we wouldn't see that. This is just an animation. So if we were to look at this picture, we may be under the impression that most of the energy present in the universe is localized along this filament of dark matter and clusters of galaxies. Something else remarkable when we look at the universe on those scales is that we realize that the further away we look at an object, the faster it seems to be moving away from us. And that doesn't tell us that there's something very specific about us, that we're very smelly and everybody wants to run away from us. What it tells us is that the very structure of space is expanding, is being stretched apart. The universe is expanding. It is the very structure of space which is expanding. The universe is not expanding into anything. The universe itself is expanding in itself. Now, there's one thing we know about gravity, which is we're all connected to gravity, and it is a gravitational attraction, which means that if it's true that most of the energy present in the universe is present through these masses around dark matter and clusters of galaxies, we would expect them to exert a gravitational attraction on each other, and slow this expansion of the universe down. Maybe there could come a point where the expansion of the universe has been slowed down so much that it will stop, and it will stop expanding, it will start contracting instead. This is possibly what we would have expected. At the very least, we would have expected the expansion to slow down. But when we look at the universe on even bigger scales, what we see is exactly the opposite. The expansion of the universe is going faster and faster. The universe is expanding at accelerated speed. This acceleration of the expansion of the universe is one of the greatest puzzles of modern physics. And it's contrary to what we would have expected if indeed most of the energy present in the universe was confined in the clusters of galaxies and the filament of darkness. So to see if that's really the case, what we can do is zoom into a completely empty region of the universe. Far, far away from any clusters of galaxies, far away from any source of life, in the middle of what we call a cosmic void. Imagine how lonely you would be there. Maybe no one to talk to, no planet around Earth. You wouldn't even have a black hole to dive into to get yourself entertained. And yet you wouldn't be truly alone. Because even in the best vacuum, you still feel with all of the quantum fluctuations and all of the particles that we know of from this vacuum bath, including that of the crust. And as we said, this should have an effect on gravity. But the effect that this vacuum bath has on gravity is very different as compared to the effect that you and me and planets and stars have on gravity. When we're thinking about the way a planet curves the structure of space-time around itself, this is something very localized. It's just around itself because it's fabric of space. But when we're talking about this vacuum bath, it's not something which is just localized at some time or at some position in the universe. It actually fills the whole space in the universe. It has done though, so since the very beginning of time. For billions of years it's done so. It does that through the whole volume of the universe completely uniformly. So what it does is not curve space-time just locally at one point. What it does is push the boundaries of space-time. There's no such a thing as boundaries of space-time. It pushes space-time as much as it can in every direction. This vacuum bath actually leads to an accelerated expansion of the universe, which is actually exactly what we are observing. When Einstein came up with the theory of relativity, he didn't know that the universe expansion was accelerated. Actually, he didn't even know that the universe was expanding. Also, he didn't know that there was such a thing as a fundamental particle leading to a vacuum bath, including that of the Higgs. But now that we know all of this, we can put those ingredients together. We can look at the effect of the vacuum bath on general relativity, on gravity, and we see that it leads to an accelerated expansion of the universe, precisely as we observe. This is the good news. The bad news is that the expected rate of this acceleration, based on the amount of vacuum energy, the amount of vacuum bath that fills the whole of the universe, is way too low. And the error is not just a factor of 2, or a small computation error that I can put to the right. The discrepancy is actually of 28 orders of magnitude. This is the biggest discrepancy, the biggest embarrassment in the whole history of science. And it's been known for a century. And this is such an embarrassment because on one hand, you have general relativity that has never betrayed us, that predicts everything we have observed, including gravitational waves and black holes, to an incredible precision. And on the other hand, we have this vacuum path coming from particle physics that has also never betrayed us. It's been detected the Higgs, and we have understood the standard model of particle physics to an incredible precision. Both of them have never betrayed us, and both of them correspond to the pillars of modern physics. And yet we
slight
put those
left,
two
into
things
sudden
together
straight right,
and we get the
30,
biggest
turn,
discrepancy
open
in the
left,
whole
onto
history
tarmac,
of science. So what went wrong?
120,
I don't know. I really don't know. Is it our understanding
turn
of this
right,
vacuum
onto
bath,
gravel,
how
and
the
crest,
fundamental
50
particle that
crest,
affect this vacuum bath incorrect?
and slight
Or
left of
is
crest,
it is
very
effect
long,
on
slowing,
gravity on
and
the
late
larger
3 right,
scales
long,
of the universe?
into crest, into 6 left,
In fact, Einstein's theory of general relativity has never been proved
crest,
on such large
into
scales.
5 left,
So that's a
80,
possibility. Very few possibilities have
jump,
been
90,
proposed.
slowing,
And the one I like to
right of the
raise,
crest, 40,
it's a crazy
left,
one, I
tightens,
raise it anyways, is that
40,
maybe
2 right short, 50,
rather than needing to take all of this vacuum
late,
bath
1
quite
left,
so
don't
seriously
cut, 30,
over the whole history of our
right,
universe,
opens,
over billions of years, and over the whole volume of
6
the
right of the
universe,
crest,
gravity doesn't need to be
late
quite
5
so
left,
serious.
over the crest, don't cut, to 2
The
right
possibility I
short,
like to
80,
raise is to say, hey,
right of the
gravity,
crest,
time
60,
to relax. In Einstein's
5
theory
left,
of general
through dip,
relativity,
30, crest,
the gravity,
100,
like
6
the
right of
photon,
jump,
is a massless particle,
caution, and 6 left,
which means that
big
it has
jump,
an infinite
70,
range.
small jump, 60,
What this means is that technically,
slowing, crest,
two objects,
40,
like two
2 left,
galaxies,
and 4
located
right,
on the other
30,
side of the universe,
slowing,
one
slight
another,
left,
that is located 10,000 million trillion kilometers away from one another, still exert a
50,
small
slight right,
gravitational
half long,
attraction.
50,
Even more remarkable, to understand the
5
dynamics
left
and the
of a
dynamics of the
bump,
whole
30,
universe, we
3
also need to
left,
account
keep
for
it
all
into
of the
bump,
vacuum
and 6
bath
right
that
of the crest,
fills
long,
the whole of the
50,
universe. But maybe this is just too much to ask.
square right,
Could it be
early 3
that the
left,
gravitational
50,
attraction that we
right
share,
short,
you and me, we can feel it, and that we share with the
to
Earth,
slight left,
and with the
30,
Sun,
unseen,
and with the galaxy,
square left,
and even with
30,
a local
crest,
cluster of galaxy,
and 3
is
right,
only
half
present
long,
because we are sufficiently close to one another.
into crest,
Could it be that we
slight
don't
left,
share
30,
the same gravitational attraction
right short,
with
keep
objects
in, 60,
and with
6
the
right
vacuum
of the
bath
crest,
located on the other side
Four
of
left
the
sharp,
observable universe,
5 right
some
over
10,000 million trillion kilometers away from us?
and slight left,
In
very
practice,
long,
what it would mean is that we would need to weaken the
to
range
6 right,
of
short
the
of the crest,
gravitational
and slight
force.
left of the crest,
We have a demonstration here how it looks like. I'm sure we've seen such a thing before,
left
like
of
a
a jump,
trampoline surface.
slowing,
You put a
70,
mat at the
slight
center
right,
and you
to
see
6
how it
left of the
deforms
crest,
the structure of
50,
this surface.
rough,
This is
hairpin
more or less what we
right,
had at the beginning with a few caveats. What we like to do here
and 4 left,
is
opens,
restrict
50,
the
as
range of the
junction,
gravitational force such that if you have a mass,
square left,
it only
tightens,
affects
and
some
6
given
right,
neighborhood.
into slight left,
and so two masses located very far away from one another,
slight
technically
right,
they
into
would
crest,
stop having
30,
a
5
gravitational
left,
attraction to
half
one
long,
another.
narrows,
More
40,
importantly, we no
short,
need to
5
account
right,
for all
5
of
left,
the
50,
vacuum bath of the Higgs and all of
turn,
the other
square
fundamental
right, onto
particles
columns,
to
30,
account for the dynamics of the universe and this
square
huge
left,
accelerated
right short,
expansion
don't
of the
cut,
universe.
and turn square
So what we need
left,
to
30,
do is understand how to
3 left
restrict
short,
or
don't
weaken
cut, and
the
3
range
right,
of the
opens,
gravitational force. But that's easy.
into 5 left, don't
Nature
cut,
has already told
30,
us how to do
4
that.
right, don't cut,
Nature has already
3
told
left
us
short,
that the
40,
weak force is weak.
1 right, onto
Because the
tarmac,
Higgs
into
mechanism
crest, and
has
2
weakened
left,
the
long,
range of this force by giving a mass to the fundamental particles that
3
carry
right to the crest,
this force,
half
the
long,
W and the
90,
Z boson. So in making the W and the Z boson massive
Slight
particle,
right,
we have
40.
restricted the range
6
the-
left,
is the
tightens of the crest,
operation
turn 5 right,
of the
onto
weak
gravel,
force.
half long,
So in
tightens,
principle, all we need to do
into crest,
is the same
so
thing
then
for
3
gravity.
left, 40,
Either we need to restrict the range of
3
gravity
right to the crest,
of your
30,
force if you want,
left,
or at the more fundamental level, what we
and
really
to
need
right,
to do is
opens,
understand how to give the gravity
right of the
balance.
crest,
And this is an extremely
So then 6
natural
left.
question. It's so natural
And to
that
right,
even Newton
cut,
himself
and 3
contemplated this
left,
possibility
and
at the
right.
level of weakening or limiting the range
To 4
of the
left,
Newtonian
cut,
gravitational
30.
force. And many other
3
amazing
right, sharp
scientists
of the
since
crest,
then,
into 5
including
left,
Laplace.
40.
And then when
5
we
right
understood
short, 50.
that gravity could also be carried by a fundamental particle
6
and that
left
was
of the crest,
related
90.
to Einstein's theory of relativity,
Slight
and
left
we
of the crest,
understood that
50.
limiting the range of
5
gravity
left
was
short
really
of a bump,
corresponding
left
to
of the
giving
crest.
a mass to the graviton.
4
This
right
has
of the
been
crest,
explored by
50.
many different scientists in the past century,
Slowing,
including
6
by
left,
Pauli,
and 5
who
right,
is one of the
tightens
founders
into 4
of quantum
left,
physics,
4 right,
including
caution,
Salam,
square
who is the
left,
same
don't
Salam
cut, 4
responsible,
right,
one of the
opens,
founders of
5
the
right to
electroweak
the jump,
theory,
don't
and
cut,
one of the
50.
fathers of the standard model of particle physics. And many other amazing scientists
left of the crest,
since then have been
40.
exploring the possibility
Slight
of
right,
thinking what
slight
it would
left,
mean
slowing,
to restrict
90.
the range of gravity or give the gravity
Turn,
mass.
1 right, 30.
But this possibility has
Short
always
of the
been
jump, to slight
entirely
left, bad
refuted.
dip, 40.
And not because it contradicts
5 right,
observations.
tightens, into
Quite the
3 left
opposite,
short,
it could help
and crest,
with
50.
observation of the accelerated
3
expansion
right short,
and reconciliate
into
the
left of the
amount
crest, to 4
of
left sharp,
energy
30,
contained in the
3
vacuum
left,
blast and
through
the
dip,
expected contribution on the
into 3
accelerated
right of the crest,
expansion.
don't cut, 90.
Now, this possibility has always been entirely refuted because it
5
was
right,
impossible
short of the
to make
crest,
it
into
work
6 left, and
theoretically.
5 right, tightens, into slight
Looking
left,
at the
and 4 right
literature
short,
for the past
slight
century
left,
on the
into
topic,
big
this
crest,
is what
60.
we read. No way, inconsistent,
Slight right,
impossible,
into left of the jump,
instability,
slowing,
and what I love
100.
most of all is
Later,
fake
keep tapping
biases.
left, short,
Now, a ghost, this is a scientific terminology, this is not me.
into 6 right, tightens,
A
square,
ghost is
into
the
crest,
most
into 4
terrifying
left.
thing that you can ever imagine. A ghost is a
right,
particle
tightens of
with
the crest.
negative energy, which would
3
make
left short,
the
and left of the
whole
crest, 30,
universe,
square right,
and you and me and everything living in it, even the very structure of space and time, decay instantaneously.
and
So
slight left,
clearly, if
into
we
right
have
of
a
the crest,
theory of
7, 5
gravity,
left, into 6 right of the crest,
theory of
60,
gravity, we need to find a way
slowing,
to get
6
rid of
left,
this ghost
half long,
or to trap
50,
it.
turn,
And
square right,
this is what
onto
has been made
tarmac,
possible to these two incredible
30,
gentlemen,
5
Frederico
right,
Barazzi
open to
and
the crest,
Andrew.
80,
In practice,
small
the
crest,
trap that we
50,
engineered
5 right,
looked
80,
much more like an Asian stair,
unseen,
or
3 left,
Penrose
opens,
stair,
40,
where we
5
trick
left,
the
pass
ghost
junction,
to
120,
live in a constrained space.
6
Why
right,
can't
tightens
it
to the
do
crest,
no harm?
and 6 left, 30, 4
This is
right to the
symbolic.
crest,
The
100,
real curve uses lots of mathematics,
4
but
left,
the
keep
result
in,
is the
5
same.
right short, 60, slowing,
And
6
to my
left
mind,
to
that
crest,
trick was
60,
pretty cute in
rub,
itself,
turn
but we
square
soon came
left,
to realize that
don't
having
cut,
one mathematical bulletproof
right to the crest,
proof
60,
for
6
the absence of
left,
this
80,
ghost and the consistency of the theory of massive gravity would be enough. But soon enough we realized that was never
unseen, 2 right,
sufficient to convince
30,
the rest of
4
the
left short,
scientific
30,
community.
slight right,
To be sure, science and mathematics,
5 left,
mathematics in
30,
particular, does imply
crest
so if
to
something is
5
proven
right,
in
to
one
5 left
mathematical
of the
language,
crest,
it has to be true.
slowing,
But even
and
in
6 left,
science,
into
there's
crest,
lots of
turn
different
square right,
scientific
40,
culture
right to the crest,
and different
40, 4 right sharp,
mathematical architectures and scientific arguments that people feel more or less comfortable with.
into sudden 3 left, 50,
So over the years, every
left,
time a new
60.
colleague had a different perspective, we were compelled to
left of
learn
the
the
crest,
language
to 2 right short, into
translate
6
a
left,
logic,
over bump, 40,
arguments
hold, 3
to their
right,
way
keep
of
in,
thinking.
into crest, into 3 left,
And we have to repeat
40,
this process
then
years
4
after
right,
years after
tightens
years
of the crest,
until there remain no unanswered
and 5 left, sharp
The
of
theory
crest,
about
and
massive
6
gravity
right,
wasn't
through
judged
dip,
by
to 5
a
left,
closed jury
40,
of 12 peers. It was
3
judged
right,
by the whole
into bump, 60,
multicultural scientific community.
6 right, crest, tightens, 30,
Overcoming that process, though, was never the aim. It was
slight
just the
left
start of
crest,
the journey,
to sudden slight
one
right,
which would
100,
finally allow us to test gravity,
finish,
completed
and
with
head
Einstein's
left
theory
to
of
stop.
general relativity.
Okay,
So if the graviton could
13
have a
minutes,
mass after all,
1.6.
what would be its value? It'd be tiny, 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 tiny. We wouldn't want this distance to be as small as the subatomic scale, like the weak force, for instance. That would be just silly. We need those distances to be very, very large, which means the mass of the graviton to be very, very weak. If we put the graviton in a normal particle scale, if we were, we wouldn't measure anything. It would be lighter than all of the massive particles that we know, including the neutrino. So instead, we need very precise instrument to measure the mass of the graviton. And gravitational waves interferometer may be able to play that role in the future, including the LISA space mission that will allow us to detect gravitational waves with a very long wavelength, very small frequency. If you think of them as color, you're going very much towards the red and beyond. For a specific event, on the top is the type of signal you could expect to have if the graviton had no mass. While at the bottom is the type of signal you would get if the graviton had a large, large mass. The effect is very much strengthened because we dramatize it, making it very large. You see that the signal appears more compressed because gravitational waves of different frequency, different color, travel at different speed. So in future experiments, by comparing our expectations with actual observations, we should be able to put a constraint, and even better constraint, on how light or heavy, massive, I should say, the graviton mass is. Whether the theory of massive gravity developed by my collaborators and I will survive the test and be relevant at all for nature is for future generations to tell. But the possibility is now open. For now, I just want to contemplate the fact that right now, in this room, it can be day or night, I don't even know, clear or cloudy, I don't know. The gravitational waves are reaching us from the depth of the universe. And with them, they carry the most precious and important messenger there is. Detecting them and understanding them will allow us to understand if and how we connect with objects on the other side of the universe, some 10,000 million trillion kilometers away from us. They will allow us to understand whether the infinitely small fluctuations from all of the particles that we know can have an effect on the biggest scales of the universe, possibly dictating its acceleration. And to me, this is remarkable because gravity is the weakest force there is. While we have detected gravitational waves, we will never, ever detect a single graviton. What fascinates me the most about her is that she perfectly illustrates how the most subtle and discrete and shy particle there is can, through nothing other than sheer persistence of the billions of years of existence of our universe, and cohesion with her gazillions of friends, be the most important element in the whole universe. She's the one setting space and time alive, the one responsible for the whole evolution of the universe, the creation of a galaxy, the formation of a home, and will be the one ultimately determining our own fate, that of the whole universe, and everything living in it. So I'll stop here. Thank you. In practice, the trap force, for instance, that would be just silly. We need those distances to be very, very large waves. We will home, and it will be the one ultimately determining our own fate, that of the whole universe and everything living in it. So I'll stop here. Thank you.
Start. Right, 30. Good luck. Five, four, three, two, one, go. And 3 right, onto tarmac, 30, 6 left crest, into 6 right, 40. Turn 3 left for crest, 90. Caution, 6 right, long, tightens. Into slight left for crest, 70. 3 left short, cut, 40. 6 left, slowing, 30, turn, 1 left, 60. 4 right, 30. Starts 3 right, 30. Good luck. 5, 4, 3, 2, 1, go. And 3 right, onto tarmac, 30, 6 left on the crest, into 6 right, 40. Turn 3 left, for crest, 90. Caution, 6 right, long, tightens. Into slight left on the crest, 70. 3 left short, cut, 40. 6 left, slowing, 30, turn, 1 left, 60. 4 right, 30. Long crest, onto cobbles. And late 4 right, half long, 50. Late 4 left, tightens, 40. Crest, slowing, 80. Turn square right, crest, onto gravel. 30, 5 left, 5 right, with a bump, 60. Left of the crest, slowing, 100. 2 right short, 70. 6 right, tightens of the crest. Into crest, caution, sudden, 1 left, half long, opens, 6 left of the crest. 140, keep left, past junction. And late 5 left, over crest, 30, long crest, 50. Crest, to 6 right, 100. Slide left, 100. Crest, 90. Right of a jump, 40, 5 right, slowing, and crest, 30. 2 right, tightens of the crest, 40. 4 left, half long, 50. Slight left of the crest, 40. Turn 4 left for crest. And 4 left, tightens, 50. 1 right. 30, slowly. 1 right, half long, 30, 6 left of the crest, tightens 3. 90. 3 left sharp, 50. Turn 1 left short, widens onto tarmac to slight right, 60. Bridge, 50. 6 right, half long, 80. Leave 4 left, half long, don't cut. 60. 6 right, half long, tightens, slowing, 70. Turn late, hairpin right, onto gravel. 100, 6 left and crest, very long. Tightens 4. Into 3 right, into crest, to 5 left, 50. 3 left and crest, 60. Long crest. And 1 right, don't cut, into left of the crest, and 1 left short, 30. Late hairpin left, and 2 right, opens. And 1 left, don't cut. And 3 right, half long, 120, slowing. Late square right, half long, 30, 3 left, don't cut, into 5 right of the crest. And slight left, 30, 6 left, into 4 right of the crest, into square left short, and slight right, 70. 5 right of the crest, 40, 2 right, into 6 left, into crest, and late 3 left, 40, 6 right, tightens 3, 30, 1 left, 30, 2 right, into crest, 90, 4 left, into 6 right of the crest, and left of the crest, slowing, 80, 1 left, and slight right, tightens 2, and 2 left. Turn hairpin right, 50, left of the crest, 80. Over finish to stop. Okay, that's a 5-minute 31.2.
Excellent drive at the trial event. You managed to impress the sponsors that were there, and they've agreed to sell us some of their higher-end products. Good result, that.
Two, one, go. 50. 3 right over crest.